There you go, recording. All right, so today's new topic, we're going to begin with something pretty simple that we call in mathematics quadrants in the plane. Guys, I know some of you don't take notes because I encourage you to don't take notes. At the end of the day, these are the slides that you all have access to, right? But please, these, go ahead and write it down. Write it down in the notebook. Write it down in the notebook. This configuration is the quadrants of the plane. Now, in every single plane that you guys work for your entire life, you will have quadrants in the plane. What are those? What are these quadrants? Pretty simple. Look, quadrant number 1, this one right here in the corner, right? Quadrant number 1. Quadrant number 2, the one to the left, right? Quadrant number 2. Quadrant number 3, right under that one. And quadrant number 4, right to the right. That's it. Now, what are those quadrants for? All right, those quadrants are exactly to name these little corners. That's it. That is the objective of quadrants. Quadrants work or are used to name corners in the plane. That's it. That's it. Now, I can tell you, for example, that point P is in quadrant number 1. Now, how do I know one? How do I know that? Because look at that. Point number P is right there. It is exactly in this corner. So we don't call it, oh, the point P is in the corner that is to the left and to the top. No, we don't call it that way. We say in quadrant 1. All right? That's it, guys. By the way, in case you didn't know, the center of the Cartesian plane, the center, the point 0, 0, that is the center, right? 0, 0. We call the point 0, 0, we call it the origin, right? Just in case you didn't know, go ahead and write that down somewhere, please. Beautiful. All right. Now, let's begin with the introduction to polar coordinate. Man, you guys are going to love this. You guys are going to love this thing. Polar coordinates. So let's say we have this point over here in a plane, right? We have this point. The point is the point A. That is the name of the point, right? And if we want to find the coordinates of this point, well, that is pretty easy, right? That is absolutely simple. Because we know that we move from 0, 0, from the origin, we move to the right 4 units, and then up 2 units. Those are the coordinates x and y of our point A, right? These are the usual coordinates. You guys have been using this for the longest time, right? We call these the coordinates x, y, the ones that we usually use in math. These type of coordinates have a name. These are called rectangular coordinates. Go ahead and write them down. Write these down, please, somewhere. These are rectangular coordinates. Why are these called rectangular? Simple. Because if you look at the point with the 0, 0, you can kind of describe a rectangle. Kinda. You can kind of describe a rectangle, right? And that happens to every single point in the plane. So that is why these are called rectangular coordinates. But these coordinates are not the only ones that we have. In fact, you guys are not going to believe me. In fact, to calculate things in most aspects of life, we don't use rectangular coordinates. We don't use in most things of life. For example, if you are using some sort of navigation system, you guys absolutely don't use Cartesian coordinates, rectangular coordinates. We use polar coordinates. So the one that I'm going to teach you right now are the ones that we are usually going to use for the rest of our lives. Not for mathematics. For mathematics, just these ones, but for the real life. So polar coordinates. Polar coordinates are simply a different way to represent the same point, right? So for example, we can use the distance from the origin to the point R. Remember, the origin is this point right here, the 0, 0. That line from 0, 0 to the point, so this one, by the way, this is a little mistake, right? This line should be in 0, 0. I know it is a little bit moved to the left, right? But assume it is a 0, 0, right? So this line from 0, 0, from the origin to the point that we are looking for, this is the line we call R. Okay? This is the distance from 0, 0 to A, the distance R. Okay? What else do we need? All right, we need the angle of elevation, theta. What is that, man? No, teacher, please don't. That looks awful. No, 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 no. Look, please look at the screen. Look at the screen. Don't miss it. Don't miss it. The angle of elevation is this one. You ready? Look. That's it. Again. That is the angle of elevation. This one we call theta. From the x-axis all the way to the line R. This is the point we call theta. The angle we call theta. All right? This is the angle we call theta. So with these two pieces of information, we can also describe the same point A. R, the distance, and theta, the elevation, the angle. All right? So these ones are the ones we call polar coordinates. Right? These ones are the one we call polar coordinates. All right, so what would be the polar coordinates of the point A? Because we know the rectangulars are 4, 2. Rectangular coordinates, 4, 2. But what are the polar coordinates? These ones are the polar coordinates. I use a software to help me calculate the distance from 0 to A. In other words, I took a ruler. I took a ruler and measured R. Right? And that is exactly how you guys are supposed to do this. So to do polar coordinates, you guys need a ruler, right? Write it down somewhere. Please, that is one of your instruments from mathematics. A ruler. You measure from 0 to the point. A ruler. Beautiful. But we also need the angle of elevation. In this case, this angle is theta equals 26.57 degrees. Look, I'm measuring this angle with degrees, right? And how did I measure this angle? Again, I used a software. But in case I was doing this in a piece of paper and using a pen, I measured this using a protractor, which is the second instrument you guys need for polar coordinates. Again, we need two instruments. In the chat, please, what are the name of those two instruments? We just said it, right? Nobody? Thank you, Aleja. And thank you, Juli Parra. Yes, we need a ruler and a protractor. That's it. We need a ruler and a protractor. That is it. Beautiful. Rodriguez, yes, that's the one. All right, let's continue. Let's continue. Now, how do you write these coordinates? This is how you find them, right? But how do you write this in a quiz? Let's say we are doing a quiz and I ask you, find the polar coordinates. So how do you write the answer? This is it. Point A has a distance from the origin of 4.47, right? That is the distance. Look, that is the R, 4.47. And the angle of elevation, this little angle here, is 26.57 degrees. So the answer is parenthesis 4.47, 26.57 degrees, parenthesis. That is the solution. Every single polar coordinate is written in this form. R, theta, and those inside parentheses. This is the way you write those answers, guys. All right, this is extremely important. Remember, in mathematics, you can do a perfectly good process. But if you don't write a good answer, then you pretty much have nothing. You pretty much have nothing. All right? So it's not enough with knowing, you also need to show it. It's not enough with knowing, you also need to show it. All right, guys? Man, that was cool. All right, let's continue. Let's continue. The easiest way for us to do this is to practice. But before we practice, we're going to take a look at a video. So what I want you to do right now, guys, please, is increase the volume of the videos in your computer, all right? Increase the volume of your computer, please. All right? I'm going to do the same here. I'm going to increase the volume as much as possible. so that you guys can listen as better as we can, right? But please, guys, this is not gonna sound perfect. So please increase the volume, all right? So you guys ready? Can I continue? Beautiful. Thank you, guys. All right, here we go.
This video is meant to be an introduction to polar coordinates. First, let's review standard Cartesian coordinates. You've probably worked with these quite a bit. When you write down the coordinates of a point as x comma y, the first coordinate is telling you the horizontal displacement from the origin, and the second coordinate is telling you the vertical displacement. So for example, the point 3 comma 2 is where you would arrive if you started at the origin, moved to the right 3 units, and then moved up 2 units. Similarly, negative 2, 4 is where you arrive when you go 2 steps to the left, 4 steps.
Do you want me to put subtitles? Okay. There.
Up from the origin, and 1, negative 3, 1 step to the right, and 3 steps down.
Right, so these are the usual coordinates, right? Can you tell me in the chat what are the names? What is the name of these type of coordinates? Can anybody?
Rectangular coordinates.
Beautiful, brother. Yes, rectangular coordinates. That is it. All right, let's continue.
Using Cartesian coordinates is very easy to describe vertical and horizontal lines.
By the way, this can also be named Cartesian coordinates. Usually in most books, we call them rectangular, all right? So if you find rectangular, you know what we're talking about. But Cartesian makes reference to the Cartesian plane. So these are Cartesian coordinates. The other coordinates, the polar coordinates, make reference to the polar plane. But these are just names, all right? You don't have to remember the names. These are just names.
And they're simply the set of points for which one of the coordinates is constant. But you could imagine using different information to describe where you are in the plane. So we could let r stand for the radial distance from the origin, and we could let theta represent a direction as measured from the positive x-axis moving counterclockwise, and we're going to measure in radians. Now we'll notice that the positive x-axis could be described either as theta equals 0 or as theta equals 2 pi.
All right, let me go back a little bit because the guy said something important that I didn't notice. All right, look here. As measured from the positive x-axis moving counterclockwise. All right, so what the guy is saying here is that give me a second. What the guy is saying here is, take a screenshot of this. There. What the guy is saying here is that every single angle, and I'm gonna draw it with red. Every single angle begins from this line over here, from the x-axis, this line, all right? That is the line from every single angle that we're going to measure. And we're gonna measure it up. So for example, this point, if we wanna do this point right here, this point, right? That point, then we have this angle of elevation theta, right? Counterclockwise, this word counterclockwise makes reference to going in the opposite direction of the clock. Now, I know a lot of you don't have a usual clock, right? You guys have this cell phone, and that is where you look at the time, right? But in a regular clock, the hands of the clock move in this direction, right? One here and then over there, someone like this, right? The usual clock, the hands move in this direction, right? Okay, this is called clockwise because they move in the direction of the clock. But look, our angle is going in the opposite direction of the clock. So we call this counterclockwise, right? This is the usual way we measure degrees or radians. We measure any angle. Counterclockwise, in other words, going upwards. All right, guys? Beautiful. Let me erase all of this. This is what the guy said there, and I wanted to make a quick intervention about that. All right, let's continue.
We're going to measure in radians. Now we'll notice that the positive x-axis could be described either as theta equals 0 or as theta equals 2 pi. All
right, here, another something important. Notice how every single angle here that the guy is describing does not have the little ball, the little circle, meaning this is not degrees, this is radians, right? The ones that we saw the past class. Now, if I ask you right now, how much is pi over 6? Then most of you are not going to know. And that is okay because we are not familiar with radians. We are not familiar with radians. We are familiar with degrees. So the first step when working with polar coordinates is changing from degrees to radians. I'm sorry, from radians to degrees. Now, how do we change from radians to degrees? Just by using a little formula, right? We just use a little formula. In case you didn't know, again, let me do a new screenshot. No, but you did know what this. Maybe you forgot it. But in case you forgot it, this 2 pi is in radians, right? How much is 2 pi? How much is 2 pi in degrees? Can anybody say it? 0. All right, 0 degrees. Sure. This guy is fast. Where are you, Marino? Where are you? Okay, that's pretty smart. Yes. But also 2 pi is 360 degrees. Right? If you guys use the formula, 2 pi is 360 degrees. What we are doing here is saying that an angle of 0 degrees, so no elevation, please pay attention to this. No elevation, meaning we are not going to move from this line. We are not going to move it. We are not moving from this line, right? We are not going to move from this line because we don't have an elevation. An angle of elevation of 0 is the same as an angle of elevation of 360. And it makes sense. Look, if I elevate 360 degrees, so exactly there, we came back to the same line. Did you see? Did you see what happened or not, guys? All right, Alba got it, because Alba is moving his head. Thank you, Rodriguez. Nobody else, maybe. All right, thank you, Moreno. All right, thank you, Paro. All right, guys, all right. Some of you are actually said yes. Beautiful. So yeah, that is the point here. By the way, in case you didn't know, 360 degrees means go around the circle once, right? A full circle, right? If I continue, if I do 2 circles, then 360 times 2, because 2 circles. If I do 3 circles, then times 3 circles, and so on and so forth, right? All right. So that is exactly what is happening here. That is exactly what is happening here. Let me erase all of this. The guy said, this is a redundancy. 0, what do you mean 0 is also 2 pi? What do you mean 0 is also 2 pi? Well, it is not. 0 and 2 pi are 2 different names. 2 pi is 6 point something. So these are not the same name, the same number, sorry. But in the plane, 0 and 2 pi represent the same thing. And that happens to every single point. Let's continue with the video.
So there's a redundancy here, but actually there's a redundancy everywhere. The coordinates theta and theta plus k2 pi represent the same direction for all integer values of k. Let's look at an example.
All right, pay attention to this example, please.
Where is 4 comma pi over 3? So the radial distance from the origin is 4, and our direction is going to be pi over 3 measured from the positive x-axis. That means this is the point we're describing.
Remember, guys, r is the measure from the center to the point, right? So we have a measure of 4. How did you find this 4? Using a ruler. You use the ruler, you center it at 0, and you measure 4. There you go, over here. Now, this 4 can be in this direction, or this direction, or this 4 can be in many directions. So the perfect direction, the exact point that we're looking for, is given by this theta, pi over 3. In this case, pi over 3 is exactly here. This is pi over 3. So this is why the guy knew this is the point. But in case you don't know where pi over 3 is, well, you change it to degrees. pi over 3 is exactly 60 degrees. So you take your protractor and measure 60 degrees. All right?
But as we saw, polar coordinates are not unique. So let's explore this example some more. Here's how we originally thought of this point. Pi over 3 radians from the positive x-axis measured counterclockwise and then 4 units away from the origin.
Beautiful. That's pretty simple so far, right? R and theta. Pretty simple.
But we could add 2 pi to the direction coordinate. And that means we'd circle around and then arrive at this direction. And then, of course, move 4 units out. So 4, 7 pi over 3 are also polar coordinates of the same point.
Did you see what the guy did right there? Did you see what the guy did right there? Instead of going up just 60 degrees, so pi over 3, instead of going up 60 degrees, pi over 3, the guy also did a full circle and landed exactly on the same line. So that is 60 degrees because of this part plus 360 because of the full circle. That is why the guy is saying pi over 3, the first 60, plus 2 pi, 360 degrees. This is this circle over here, 7 pi over 3. We just add this regularly, 7 pi over 3. Now, how much is 7 pi over 3 in degrees? Well, this is 60 plus 360. So this is 420. This is 420 degrees, right? So that means we have 2 ways of describing the same point. We can describe it as 4,60 degrees or 4,420 degrees. And right there, we have 2 ways of naming the same point. Write this down somewhere, please. The points in the polar plane are not unique. We can name the same point in different ways. And this is just if we take 1 circle. But what if we do 2 circles? What if we do the first 60, then 1 circle, right? 360 more, and then another circle, another 360. That will be pi over 3 plus 4 pi, right? Because we're doing 2 circles, 4 pi. Huh? That is also the same point. So we have a different way of calling the same point. Did you see? All right, let's continue with this.
But we could also subtract 2 pi from the direction coordinate and obtain negative 5 pi over 3. So in this case, we would travel 5 pi over 3 units clockwise from the positive x-axis and moving 4 units out once again, arrive at the same point.
Beautiful. Let me tell you something real quick right now. Whenever we're talking about polar coordinates and you find a negative number, right? This is going to happen for the degrees, for the angle, or this is going to happen also for the r, for the measure of r. We can have these 2 be negative. Now, what do we do when we have a negative angle? Well, instead of measuring upwards, we're going to measure it downwards. That is the idea of a negative in here, all right? Write it down. Write this down somewhere. A negative in polar coordinates, again, I'm going to tell it again. Write this down somewhere. A negative in polar coordinates means measuring in the opposite direction. Again, a negative in polar coordinates means measuring in the opposite direction. So that is exactly what we're doing here. That is exactly what we are doing here. Look, we have some amount of degrees. This is 5 pi over 3. To be honest, I have no idea how much this is. All right, let me do my calculations real quick. This is 300, right? This is 300 degrees. 300 degrees. But we have it negative. If you use a protractor, I assure you, you will not find a negative 300 there. You're not going to find it. So if you were not paying attention, you will not know how to measure a negative degree. But now you know. It is the same 300, only that instead of going up, you're going to go down. All right, this is negative 300 degrees. And look at that. In this case, instead of going up 60 degrees, we went down 300 degrees. And we are still landing on the same line. So this is a different option for degrees. We can add 2 pi, so add circles to the angle, or we can go backwards. All right.
Here's a sneaky possibility. We could add pi to the coordinate pi over 3.
Did you see what happened? All right. By doing this angle,
So
4 pi over 3, these are just random angles that the guy is giving, all right? The guy decided to measure 4 pi over 3. Look, positive, right? Positive 4 pi over 3, so upwards, counterclockwise. We landed here. But that is a difficulty, right? That's a mistake. Because we wanted to land in this line, right? This is where the point is. So we would think this angle doesn't work. We have to find a different angle. But take a look at what the guy is about to do. Pay a lot of attention, please. Take a look at this.
sort of pointing in the opposite direction, which might seem like a problem, except if we back up by taking r to be negative, we once again arrive at the same position.
Did you see that? So the angle is positive, but the r, the measure of r is negative, meaning instead of measuring 4 in this direction, again, the direction that was given by the angle, we always measure in that direction, right? This is the direction given by the angle. We should measure 4 here. The point should be located here. Look, 1, 2, 3, 4. This should be the position of the point. But since we are looking at negative 4, we are going to measure it on the opposite direction. So not like this, like this. We are going to back up. So look at this. 1, 2, 3, and 4. Did you see that, guys? Negatives in polar coordinates means we measure backwards. We measure in the opposite direction. So here, these are perfectly good polar coordinates. They might seem like they're not, but they are.
So here's a pretty non-standard way to do it. Usually, when you're describing points in the plane using polar coordinates, you try to use a positive value of r. But it's important to interpret what happens when r is negative, because you will often have to do so when you're dealing with polar equations. So this is yet another way to describe the very same point in the plane. Polar coordinates are non-unique. There are infinitely many ways to describe the same point.
There are infinitely many ways to describe the same point. We have infinite. Here we just named 4. The guy just did 4. Four ways of describing the same point P. But all you have to do is pick one of these. Pick one of these and add a circle. That's it. You have a different way. You have a different way to describe the same point. So instead of adding one circle, add 2 circles. For example, to this one, add 2 circles, or 3 circles, or 4 circles. So we have infinitely many ways to describe the same point. All right? Beautiful. That was the video for today. We can continue with the video, but we're going to do it the next class. The next class, we're going to talk about a lot of other things. For now, let's continue with the presentation. All right. Now, I'm not gonna leave you alone for this. All right, we're gonna practice a lot of this. So let's begin by practicing the first point. Plot this point in the polar coordinates, in the polar plane. All right, using polar coordinates. We're gonna plot this. All right. Now I am recording this class, so in case you don't understand something, you can always go back and watch the video, or you can tell me, please, teacher, can you explain that again? Just the usual drill. All right. Here is how we do it. First, we recognize that we don't know where 5 pi over 3 is located. We don't know where this is located. We don't know it. We don't know it. So we change it to radians, right? to degrees, sorry. Now, here is the formula for degrees. We change from radians to degrees. This we saw the last class, right? Instead of 5 pi over 3, instead of 5 pi over 3, we put it instead of the radians, right? We replace it. And then do the calculations. Here we can cancel the pi. So 5 times 180 over 3. We can do this in the calculator. And we have that 5 pi over 3 is 300 degrees. So maybe that makes things easier now, because if we have a protractor, which by the way you guys should have right now, because this is one of the materials of mathematics, right? You should have a protractor. So now we can calculate, we can plot this point better. Instead of doing 5 pi over 3, which is kind of awful, kind of just bad looking number, we can now do 300 degrees. And this is exactly how it will look in the plane. Look, always begin by plotting, the degrees, always. In the Cartesian coordinates, so the usual ones, the rectangular coordinates, we began by doing first x and then y, right? That is what we did all in the past. First x, then y. But in this case, these are polar coordinates. Begin by plotting the degrees first. So take out a protractor and measure 300 degrees. 300 degrees, so measure 300 degrees. Beautiful. So this is the direction here. Now, to measure the tree, just take a ruler and measure from the center in this line. There we go, right there. Right there is the measure tree. So we have our first point, A, which is 3,300. That's it. 3,300. That is it, guys. All right, let's do another one. How about 2, negative pi over 4? This is a negative. This has a negative number, right? Again, same process. We use the formula to change from radians to degrees. From here, we know that negative pi over 4 is negative 45. So this is the angle that we need to measure now, negative 45 degrees. This is what it will look in the plane. Since the angle is negative, we are going to measure it downwards. Clockwise. Downwards. This is the angle now, right? Negative 45 degrees. From here, we just measure 2. How? Well, we use a ruler. Take a ruler and from 0, 0, we measure to the point B. There we go. That is exactly the location of the point B. That's it. 2, negative 45 degrees. Can we do it with this one, 3, 0? Yes, we can. The first thing to recognize is that the elevation is 0. So we don't have to do a lot of things here. We can just jump right into the plotting because the elevation is 0. Just in case you still want to do the same process, just change the radians by 0, put it in a calculator, and you're going to find that 0 radians is 0 degrees. This isn't necessary. This is not necessary. We knew the elevation was 0. But how do you represent an elevation of 0 in the plane? This is how. No elevation at all. Look. The point is exactly on this axis. Because we haven't elevated the point. This is exactly the location. We just measured the ruler. We just measured the increase of R with a ruler. 1, 2, and 3 with a ruler. That's it. This is the point C, 3, 0 degrees. Beautiful. How about these ones? Negative 2, pi over 4. We have a negative now here. Can we measure this? Yes, we can. Yes, we can. This is how. Again, begin by doing the same process, changing radians to degrees. The formula, changing radians, we have degrees now, so the point is negative 2, 45 degrees. Remember it, guys. This, we can do it with the calculator, and it's extremely simple to do with the calculator. But in case you don't have a calculator, we can always just cancel the pi and then divide 180 divided by 4. That's pretty simple. All right. So how do we measure this angle? This is how it will look in the plane. So 45 degrees, remember, always begin with the theta, with the angle. 45 degrees is exactly here, exactly in the middle of the quadrant, exactly in the middle, there. 45 degrees, right? And now we are going to measure 2, right? So 1 and 2. No, the point shouldn't be here because we have a negative a negative r, right? The distance this time is negative. So we are going to measure that distance in the opposite way. Remember, negative polar coordinates means opposite direction. And yes, Samuel, we all saw that one. Yes, we saw it, Samuel. All right, let's continue. So 1 and 2, that will be the point D. Measuring on the opposite direction. This should be the direction. This one, this was the direction, 45 degrees. This was the direction. So in the opposite direction is this one over here, B. All right, guys, this was all the practice that I have planned for you today. All you have to do right now is get to do it yourself. So please, in your books, locate the page 725. 725. Locate this page and get to work on these exercises. As usual, if you cannot do 1 or 2 or any amount, ask me and we will do them together. All right, I will show you my board and we'll do it together. All right, guys, this is what we're going to do all the way up until 10 in the morning. So I'm gonna cut the video here. I'm gonna cut the recording.